Hello everyone, I'm Yuting Yang and very happy to be here to share our work, Epsilon Weakened Robustness of Deep Neural Networks. This is the outline of my talk. First, we briefly review the concept of adversarial example of neural networks. The state-of-the-art models can be easily fooled by small perturbations. For example, a visually imperceptible image perturbation can cause a neural network misclassification. From the view of logic, we can describe the robustness of a deep neural network F with a first-order formula like this. This formula is defined under a universal quantifier. That means F always outputs right decisions for all the inputs in a number. If this formula holds, the network is absolutely safe on this input space. However, this definition is migrated from traditional software theory. As machine learning-based software are very different from conventional software, so we try to rethink the difference of their foundation and rebuild the theory of robustness for machine learning-based software. We can imagine that for a traditional software, if a program reports that his program has no bug, his boss will appreciate his job. However, if we report that we create a deep neural network model has no bug, and the accuracy is 100%, I think the boss will say, there must be something wrong with your program. Go back and check it carefully. Because no bug is the biggest bug for a machine learning-based software. We'd like to consider two tasks. The left one represents traditional software and the right one represents machine learning software. These two tasks are recognizing palindromic sequences and handwritten digitals. They are both pattern recognition problems. For palindromic sequences recognition, we need to give a procedure or Turing machine to recognize them. For handwritten digitals, we need to find a neural network model F to recognize it. It seems that there is no much difference in the view of task and goal. From the logical view, we try to discuss correctness and completeness for traditional software. In machine learning, things become different. We no longer discuss correctness and completeness. As an alternative, we discuss accuracy and generalization. Accuracy is an alternative of correctness, and the generalization is an alternative of completeness. They can be viewed as a quantitative version of correctness. For traditional software, if our program cannot give a correct output for an input, we will say there is a bug. However, if a programmer claims that the accuracy of his neural network is 100, we may say something must be wrong. What caused this difference? We think the fundamental reason is that the formal language of input X is usually undefined for machine learning tasks. We can define the formal language of palindromic sequences. Take handwritten digital one as an example. Although we can define the carrier of information like matrix pixel, but we cannot define the concept itself like what is 1. I also think this is the most advantage of neural networks. They are good at dealing with things that experts cannot formalize. If we consider robustness merely under universal quantifiers, some inconsistent phenomenon may arise. For example, the safe region that we can analyze is in a normal, but it is much smaller than the real safe region in high-dimension space, and the real safe region is usually non-convex, and we cannot compute it exactly. Besides, the safe number is very small, so that a drop of rain on the input camera will shift the input outside this region. Sometimes, if the given point is located near the boundary of the safe region, then we may draw a biased conclusion. More importantly, Some adversarial examples are essentially generalization errors. How can we completely eliminate generalization error and make the network safe? This phenomenon prompts us to rethink the concept of safe in the deep learning-based system. As Turing Award winner Shamir says, fully secure systems don't exist. We should establish the concept of sufficiently safe or secure. Towards the direction of rebuilding the concept of safe, we rethink the robustness from the view of quantification and propose epsilon-weakened robustness. This is the definition of epsilon-weakened robustness. We relax the universal quantifier. The formula depicts that the quantification or the proportion of adversarial examples is less than epsilon. Deciding whether this formula is true is called epsilon-weakened robustness decision problem. Compared with counting how many adversarial examples, this problem is theoretically easier. If we want to find a maximum epsilon robustness radius, we can solve this optimization problem. We can prove that epsilon robustness decision problem is PP complete. The proof sketch is here. First, we should give a polynomial time probabilistic algorithm with an error rate less than 1/2. Then we reduce the major set problem to epsilon robustness decision problem. This is a polynomial time probabilistic algorithm with an error rate less than 1/2. This is the proof. This is a diagram about how to reduce measure set to epsilon robustness decision problem. We use ReLU activation to simulate not gadget and set clause. As PP completeness indicates that we cannot give a polynomial exact algorithm, so we relax the completeness and soundness of the decision algorithm and hope that the error rate of our algorithm is strictly controlled less than alpha and beta. We designed a statistical inference method to answer the epsilon robustness decision problem based on the law of large numbers. Based on some mathematical derivations, we have the sample size of n in our statistical inference method should satisfy the last inequality. This is the decision algorithm. The right side is the computational complexity under different norms. We can only handle the case under these three norms because for other norms, we haven't found an algorithm in polynomial time yet. Here is a comparison of the traditional robustness analysis results and the epsilon robustness analysis results for a neural network. ERAN is a conventional robustness verification tool, and EWRD is our epsilon robustness analysis tool. We can see that perfect safe radius reported by ERAN are usually very small. However, if a small proportion of adversarial examples is allowed, even 0.001, the epsilon robust regions will become much bigger. These four popular networks perform the same. If a hacker tries to attack the neural network via some gradient-based search algorithms, he still has a chance to find an adversarial example out in a weakly robust area. So how to resist this attack? In this work, we designed a robustness enhancement method, which is an application of our epsilon weakened robustness theory. Adversarial examples distributed everywhere like wildfire. Adversarial training is like using water to put out fires. As the saying goes, big wildfires are never won with just water. What we need to do is to fight fire with fire. We replace the word fire with perturpation and get fight perturpation with perturpation. In this framework, we use two-stage perturbations to build an enhanced model G on the base model F, as long as F satisfies weak robustness. In the first step, we try to confirm the input X to data distribution. The second step is to apply random word substitution to X and utilize the example of samples to make a prediction. The randomness introduced in the first stage can be eliminated by this process. For an input X, we first perturb it in the direction of noise reduction. This perturbation has two purposes. One is destroying the attacker's perturbation on the input X. The other is conforming the input X to the data distribution as much as possible. The second step is voting. We can draw n samples uniformly from the perturbation space and vote. Two popular voting methods can be utilized in this process: majority voting and polarity voting. This method is simple, but we should figure out how many samples do we need. This is the relationship among the voting error rate, sample complexity, and robustness metric epsilon. If we want the error rate of the voting result to be less than some certain value eta, we have this in equation. We have that if a best classifier F satisfies epsilon robustness, the enhancement classifier G can be successfully attacked with probability less than eta when sample size n is greater than this value. In practice, we regard a network satisfy weak robustness well when epsilon is less than 1/3. Because in such a situation, we only need about 200 samples to get a sufficiently safe system, such as the attack success rate is less than 10 to the negative fifth power. These are some experimental results. PGD is a white box attack and Zo is a black box attack. As our enhanced the classifier G is not differentiable, the white box is invalid. From the table, we can see that FPP can greatly reduce the attack success rate for different models. If we use adversarial training to improve the weak robustness of the best classifier, then we can get a more robust enhancement classifier. Numerals with underlines are the transfer attack success rates, where the input is generated for the best classifier F. If we want to further improve the defense against the transfer attack, we can improve the filter used in the first step. Besides, we will show some interesting epsilon robustness analysis results. These four networks have almost the same accuracy on the test set. The first one is the norm, and the second one simulates the overfitting situation. We remove the max pooling layer, which is designed to improve the robustness of neural networks in the third one, and simulate a situation where a program forgot the normalization operation in the last one. We can see that the epsilon robustness ratio of the best network are larger than other three networks. This indicates that although the accuracy of these neural networks are the same, their quality is not the same. This figure shows that we can analyze the epsilon robustness around misclassified points and make a multi-level extension. We know that in practical applications, a neural network can make a mistake, but it doesn't mean a disaster. When a neural network mistakenly identifies a car as a truck, there may be no dangers for a self-driving system to make the decision of avoiding the vehicle ahead. We compared the efficiency of EWRD with ERAN on the same networks only for reference, as they focus on different problems. When the value of epsilon is very small, epsilon robustness will be very close to conventional robustness. As our algorithm relaxes both completeness and soundness, our algorithm will be more efficient than conventional robustness verification tools ERAN. This table shows the time consuming of our methods. For conventional robustness verification problem, the soundness methods may encounter efficiency problems for large-scale networks and datasets, Our method can be applied to larger network with more than 100 layers. In conclusion, we rethink the robustness from the view of logic and propose a notion called epsilon weakened robustness, and design a robustness enhancement method FPP to resist adversarial attack. Hopefully, our work can lead to more thinking about the theoretical basis of deep learning-based software quality. That's all. Thank you for your listening.